going to be a long, fun journey for you kids. All right, cool. So I'm going to be talking about smooth functions associated with wavelet gaps, with wavelet sets on linear space, and frame gaps. My name is Emily King, and I work with Dr. Benedetto, and he strong-armed me into giving this talk today. So this is the first time I've given this talk, so now it's being recorded for future generations. So please bear with me. Here, I'll just do this. It'll be my. So a quick outline of what we're going to do. Mainly I'm going to go over results from 2 papers with some of the background, and I'm also going to go a little bit into detail of some of the background elements because I think some of the proofs will actually kind of tie in with some of the material covered in this class. Some of you that have taken a number of MAIT courses before might have seen some of the background material, but hopefully it won't be boring. It'll be a good review. Start with a basic introduction of various ideas that we're going to need. Frame bounds and approximate identities. So a canonical example is where we first start getting into some of the newer ideas. Shrinking method to obtain frames, frame bound gaps. So we'll get through all this get started. Okay. So what's the problem? Like, how did this come up? So it's well known that for an MRA, if you want an MRA for a wavelet basis over L2 of RD, so you have higher dimensions, then you actually need 2 to the D minus 1 wavelets. So, if D is equal to 1, so this is just, wavelets over the line, then that's fine. It just says you need 1 generated wavelet. But if you want an MRA structure, then you have to, this, increases exponentially the number of wavelets you need to start with. And applications, sometimes they get around this by just tensoring lower dimensional wavelets. You take a system over the line, and then you just do that in the vertical and the horizontal. But that's not as interesting mathematically. So until the 1990s, it was actually assumed that it would be impossible to have any wavelet system for over L2 of RD, where D is greater than 1, which was generated by a single wavelet. And actually, Dye and Larson over the course of the 90s actually showed that this was false. And they did this by constructing sets called wavelet sets. So we'll get into the definition of these wavelet sets, but these wavelet sets can generate non-MRA, but single dyadic, so just a basic wavelet system with dyadic dilations and integer translations, and you only need one generating function. The neighborhood mapping construction by Benedetto and Leon and Benedetto and a few other authors provided a specific construction for such wavelet sets in various dimensions. And it's an iterative, infinite process. But if you stop that process after a finite number of steps, you get what are called parsable frame wavelets, which I'll define that wavelet set, which I'll define in a second. But these things have nice spectral properties. And what we want to do is we want to smooth these wavelets, because these wavelets that are generated by these things called wavelet sets, on the frequency domain, they're discontinuous. So what we want to do is we want to smooth that out, because if it's, I don't know if you've gone over kind of the connection here, but discontinuity on the frequency domain corresponds to slow decay on the time domain and vice versa. So if you take the Fourier transform of something, L2 Fourier transform, and you get something discontinuous, then that means what you started had slow decay. So, right. So another way of thinking about this is starting with something that's discontinuous. So if you start with something that's discontinuous and you take the Fourier transform of it, you're not going to get something in L1. So, so basically what we want to do is we're going to take these properties, these sets, which are generated by a single function, unlike the MRA sets, and they have nice spectral properties, which we do by dropping down to frames, but then we want to try to smooth them so that we get better decay. I feel weird that it's happening before I'm hitting the button. It's sort of creepy. Anyway, sorry. So just to make sure we're on the same page, basic definitions. So a wavelet, so we have some sort of function in L2 of R, so it's square interval, and we define this wavelet system with this script W, and it's a system of all dilations and translations, so dyadic powers. And here the only thing that might be different, since you're not, I don't know if you guys, how much you do in higher dimensions, but here we're translating by elements of the integer lattice, so 1, 1, 1, 0, 0, 2, so on and so forth.
So
and,
just to clarify, this K in the Z, so is that D copies of K?
Yeah, basically. So you.
They don't all have to be the same.
Yeah, and if you.
They don't have to be the same?
Well, if you think about it, so if you just look at Z2 or Z squared, then basically you're looking at all of these points where all the coordinates are integers.
Okay.
So this is going to be 0, 0. This will be 1, 0, negative 1, 0.
So it's not just the integer points along the line with slope 1 or anything like that?
No, so it's all of them.
Okay.
Now this idea can be generalized. You can use other what are called lattices, but this is the simplest case right here. You can also, since we're working in higher dimensions, and we're not going to go into this in this talk, but so in one dimension it's pretty standard that you dilate with powers of 2, right? But because if you think about it, if you're dilating with other numbers, it's kind of like the same type of idea. You're still getting the same type of shrinking of the base. But in higher dimensions, it's possible to actually do this dilation by some matrix. It's not just 2 times the identity, it's some other kind of matrix. I won't get into that, but it's something that can be done and has been done. Yes?
Since you said you won't get into it, I'll be brief.
Uh-huh.
The number out front, is that like the determinant to the power if you use matrix?
It's the square root. So yeah. So basically, the reason that number out front is there is so that if you
Keep the freaking.
right, so it preserves energy.
Yeah.
So preserves energy, preserves the inner product, unitary, however you want to say it. That's really the only reason for this constant right here. Because I mean, once you start actually using wavelets, you're going to be multiplying by constant anyway. So it seems like kind of pointless to leave that in there. But that's the reason why. It's because if you were to now take this and inner product it with itself, it would have the same norm, the same energy as it did beforehand. So that's the only reason that constant's there. But yeah, it would just be the determinant of the matrix, the square root of that. So if the system forms an orthonormal basis, then we call this psi a wavelet. Okay. So we define the Fourier transform this way, and we take this function f, we multiply it by this exponential, and we integrate. The only thing that might be slightly different if you're not used to working in higher powers is this right here. Instead of just multiplying x times gamma, we're taking the inner product of x and gamma. So just a little math mumbo jumbo, basically, that this is defined for functions in L1, but you can extend this to functions in L2 so that there's a unitary mapping, kind of one-to-one onto from L2 to itself by the Fourier transform, which is why this slow decay can come up, because if it's L1, then it's like iterable, but once you allow other functions in, it gets interesting. So okay, so examples of wavelets. You guys have done the HAR, right? That's the very first wavelet. It was like an appendix and an example in a guy's dissertation about 100 years ago. Actually, I think it's like 1909, so it's coming up on 100 years. So these two functions right here, the Shannon or little Paley wavelet and the Journet wavelet. So what's different about this is here we kind of have piecewise flatness on the time domain, but these little checks mean we're taking the inverse Fourier transform, which really we could just do the Fourier transform. It's just a weird quirk of mathematics that we denoted by this inverse Fourier transform. So basically this means on the frequency side that they're going to be flat. But then we take the Fourier transform and we are generating our wavelet. So if we have some sort of measurable set, and we take the characteristic function of that wavelet, so I guess I should clear up the notation here, what that 1 with the 2 bars means. So this simply just means the function that is 1 if your x is an element of the set K and 0 otherwise. So we have a set, and we take the function that's 1 on that set and 0 everywhere else. We take the inverse Fourier transform, and we get a wavelet. Then we say the set we started with was a wavelet set. So these two examples right here, if you cover this up and look at the set, cover this up, look at the set, these are examples of wavelet sets. So what Dye and Larson basically did is they gave these things a name, called them wavelet sets, and then showed that you could construct such things in higher dimensions and what sort of geometric rules they have.
So the Haar system does not give rise to a wavelet set.
Yeah, the Haar system is like, if you want to think about wavelets, like wavelet sets and a Haar-like system are at the opposite end of the spectrum.
Okay.
Because, well, I just erase that. But we're going from like this flat, piecewise flat discontinuous thing with the Haar wavelet on the time domain, whereas the wavelet sets are the piecewise flat, discontinuous on the frequency domain. So a lot of what's done, like Jobishi's wavelets, things like that, they're somewhere in between. You have like this continuity and some, depending on what you're using, some sort of smoothness on one side or the other. But
Yep.
and I guess I don't think if I didn't put this slide in, then I'll go back and say there's some very neat geometric properties of wavelet sets, which is why they're really interesting. It's not like, oh, these sets exist, and then you just kind of look around for them. They have very nice properties.
Several
actually,
weeks.
why don't I just do that now, since it's a good time to do it.
Several weeks ago, Dr. Benedetto gave a lecture involving tau congruence. It's got to be the same kind of stuff.
Yeah, so maybe you guys have seen all this. So tau congruence meaning that there's some partition of a set, another partition, and okay.
Right,
So,
and he showed that it was. I'm trying to think what part of. I mean, he showed it was an orthonormal basis and just left the orthonormality as an exercise, but he went through the. What did he do, guys? Does anyone remember? He left the orthonormality as an exercise. He basically did the whole proof that it's an orthonormal basis.
right.
If it's if k is tau congruent of -1 to 1 to the dth power.
Right. Right.
So we've seen that. Just to let you
Okay.
know.
And so, but you also need delta congruence, right? Not just.
He didn't mention that.
Okay. So basically, what you need here, and what is the delta congruence? So the tau congruence is that you have some. Actually, can you just go forward? Because if it's way better. It's not forward. How could I forget that? Go back. I'm sorry. I told you this first time I gave this talk. Okay, so basically a set are sets K and L are tau congruent. Ooh, I'm sorry. See, this is why I want the slides. I don't know. I am like incapable of writing on the chalkboard without it producing ear-splitting noise. Okay, so we have sets K and L tau congruent if.
You have to angle it. That's why.
Which way?
It doesn't matter. Just don't write straight.
Okay, so if there exists partition you guys know partition, right? Or do I need to review that? Okay. So we've broken up these sets into partitions, right? So such that there exist integers k sub n, or in this case we're going to do the d. Such that I'm sorry. I like making you guys erase. It's really what I like. Okay, so we've got this, and we've got integers, such that if we shift each of these pieces by this integer lattice amount, we get a partition of L. Okay, so I think I finally dug myself out of that hole, right? So we have a set K, break it up into pieces, we shift each piece by something on the integer lattice, and if what we end up getting is L, then it's tau congruent. So delta congruent So you can't show this video to Benedetto because if he saw the way that I was erasing the board, he probably wouldn't get a good PhD. So, have you ever seen it? It's very. Okay. Delta congruent. So K and L are delta congruent if there exists the partition K sub n of K such that there exists, call this L sub n, and this time these are integers, not integer lattice points, such that 2 to the L sub n of Kn is a partition. So, this definition, we are taking the pieces, breaking them up, and they're scaling them all by powers of 2. And if what we get is this, this L, then we're done. So the reason that both of these things are important, I think, should probably be somewhat obvious. When we're dealing with wavelet systems, we're translating and we're dilating. So we want both of these types of congruences. And so,
What do we mean about the pieces? Just they're measurable?
yeah, so I was kind of hand waving with that, but. And this partition is a measurable partition.
Right.
I seem to recall he made it countable. Is that important?
Yeah.
Okay.
So countable also
Yeah. Well.
is
Yeah.
kind of inferred by this n.
I was about to say.
I was doing a little bit of hand waviness just because I kind of wanted to get the idea, and but yeah. So.
And he did do delta congruence. He just didn't call it delta congruence. Now you put it up on the board. I recognize it.
Okay. Okay. So then if he went through that, then basically what we want to show is something the wavelet set, then set K in RD is a wavelet set if and only if it is tau congruent to 0, 1 to the D and delta congruent to -1, 1 to the D less -1/2, 1/2 to the D. So if you think about this, all this is really saying, and so what happens when you take this box from 0 to 1 and you shift it by all the different elements of this integer lattice? So you end up filling in all the boxes between those dots, so you get the entire plane perfectly partitioned. So similar with this delta congruence, in R2, what is its shape? We've got 1, -1, 1/2, -1/2. So if you multiply this by all the powers of 2, it's going to shrink in and fill up, or expand up and fill out. So when you multiply this by, scale this by all the dyadic powers, then you get the entire plane, except for the origin. But that is a set of measure zeros, so we pretend it doesn't exist. So basically, this is the same thing as saying we have a wavelet set if all the dyadic dilations of the wavelet set fills the plane or RD, whatever, and all of the integer translations or integer lattice translations fill up your entire space. So this is an equivalent statement that we're saying right here. Okay, so now that we've done this orthonormal basis, we're going to drop back down to a frame. So just to review the definition of a frame, comes from Duffin and Schaefer in 1952. So we have some collection in Hilbert space with a finite dimensional space, L2, whatever. So we say that this collection is a frame if there exist non-zero finite constants, such that for all f in the Hilbert space, we have this inequality here, which is a particle-like equality, or like the Parsifal's inequality, or like Parsifal's equality. It's an inequality that's like Parsifal's equality. Okay, so the maximal A and B are called the optimal frame bounds, and for the purposes of this talk, we'll be assuming everything's optimal. So from now on out, whenever you see frame bound, I mean that this B is the smallest possible B that works for all functions f, and this A is the largest possible A that works. We call A frame tight if A is equal to B. It's parsable if A is equal to B is equal to 1. And if the second inequality, so if we have this upper bound, quite possibly not the lower bound, we call this a Bessel sequence. And for the purpose of this talk, we will still refer to this B right here as the upper frame bound, even though usually in the literature it'll be called a Bessel bound. But that way we can kind of handle multiple cases at the same time. So how much, I know that you guys I think have heard the definition of a frame. Like, do you kind of have the intuition of why we use frames? Do you want me to explain that, or if is that already clear? Not really, because you went up and down at the same time.
You asked the question, I said yes to or no.
Okay. Okay, so the basic idea is sometimes for whatever reasons, an orthonormal basis or a basis, although theoretically is very, very nice, doesn't work in practice. So one idea is just a very simplified idea. You can think of frames as introducing redundancy in a system, almost like if you use an error correcting code, you're sending more bits than the information actually contains, but you're also helping protect against errors. So frames in some sense can be thought of as an error correcting code. Because basically what we're doing right here is each of these coefficients, so if we have a frame, so J for a Hilbert space, then for an arbitrary function in that Hilbert space, or image or signal or whatever, we can think of this collection of inner products as yielding a code. This is kind of hand-wavy. I'm not actually going to get into coding theory at all. But basically, these inner products encapsulate all the information that we know about the signal or the image or whatever, but there's some redundancy in there because, for example, a frame can have 3 elements for R2. So obviously there's redundancy because you only need 2 elements to span. But if we now send 3 coefficients rather than just 2, if there's some sort of noise or error, something like that, the sending using the frame is more resilient. So another reason that a frame might be used is actually in this particular case that I'm going to be talking about today is these wavelet sets for higher dimensions are orthonormal wavelet sets are very ugly. Basically, they look like fractal-like. They've got, all sorts of squigglies. And so obviously, if there's you couldn't actually use it. You can make these pretty pictures, and they have undergrads do that for their little research project, is generate little pretty pictures of these things. But like, I mean, that's it. It's just this like weird picture with, you zoom in, there's still stuff going on, so it's like a fractal-like boundary. And it wasn't until recently that it was even discovered that there even existed anything that wasn't fractal-like that was a wavelet set for dimensions 2 or higher. And even then, it's only for dimensions 2, and it's still, it's not an algorithm, it's just someone that kind of figured out a couple of examples. So in this case, if we end up restricting to what I'll define in a second, a frame wavelet set, then those are very nice. So, for example, this function right here would actually be a frame wavelet set, or shrunk down. But so, and you can kind of see why things go wrong in higher dimensions, because, for example, so let's think about what happens with in 1D. So we have the Shannon wavelet set. You really don't even have to really split this up. You can easily see that if you shrink this, it's going to tile in. As you diagonally expand it, it's going to fill out, and you're going to get, by dilating with power of 2, you're going to get the entire line except for the origin. And then as far as shifting it goes, well, 1, negative 1/2, 1/2, 1. I mean, it's very easy to see. You shift this by 1, and you get 0, 1/2. You shift this back by 1, you get negative 1/2, 0. So it's very easy to see how this is going to fill up just by the integer shifts. Now look at something shaped like this in 2 dimensions, which in some sense is a natural analog of what's going on right here. So here, we see that it's this shape right here is going to diagonally fill up the space. But then what happens if we try to shift this by an integer amount? There's no way that this inner part of the box is going to be filled without things overlapping, right? So that's kind of like a hand-wavy, intuitive reason why things start to go wrong for wavelet sets in higher dimensions. But it ends up, there are very nice wavelet sets if you reduce the frame. Okay, so wavelet frame, we're just putting all these words together. If you have the dilations and translations of a function, and it forms a frame, then we call it a wavelet frame. Okay, so this is the definition I was talking about. If we have a set, measurable set, and we look at the sequence or the collection of dilations and translations of the inverse Fourier transform of the characteristic function, and we get a frame or a type frame or a partial frame, then what we end up getting, this L, we call this a frame or a type frame or a partial frame wavelet set. And really wish I had to erase this. Okay, so a fact. And if you're interested in seeing sources, I can give you the sources for these theorems. That a parsable frame wavelet set K in R&D is, I'm going to word this awkwardly, so K is tau congruent So the only thing we've changed here is it's if we take the integer translations, it's not going to fill up the plane, right? So it still will dyadically fill up the plane, and it's less trivial to prove this the Percival result, but it makes things very easy. This result makes things easy once you have it. So one of the nice things is that, so while this right here is not a orthonormal wavelet set, we can shrink that down. Is a Percival frame wavelet set. So now, so one of the reasons in this case, obviously, when we're look at frames, is here we're getting all of these weird shapes, but all we have to do now is say, well, why don't we consider Percival frame wavelet sets and we get such nice shapes like this, basically like a boxy. It's basically this shape, but we just shrunk it down. That's really the only thing that's different about it. Okay. All right, so I'm not going to bore you guys with this, but basically just know that yes.
The Percival. I'm actually trying to remember what the exact definition of frame is. What's the? Oh, just go back a couple of slides.
Yeah.
Okay, so why wouldn't a Percival frame be an orthonormal basis?
An orthonormal basis is a Percival frame,
Right.
but not the other way around. So in finite dimensions,
Just because it might not be orthonormal, it might not be an orthonormal set.
right. So let me give an example where you can see, even in finite dimensions, how an example of a Percival frame wavelet that is not orthonormal basis. So this is what's called the Mercedes-Benz frame. So to start off with, we'll just consider these vectors. -1/2, 3/2, -1/2, -3/2. So these are just the unit vectors that are evenly spaced, the roots of unity. And it's called Mercedes-Benz if you rotate it, but I didn't. So anyway, so this is it. And if you, let me.
That's a scale that.
What? That's what I'm saying. I hadn't yet gotten Percival. So basically what happened, so I can never remember the correct scaling unless I actually work it out, so that's why.
Should be like 2/3.
But it's like root 2/3, I think, maybe. Yeah. So it's just better, it's more instructive. Okay, so we just take some arbitrary vector in R2. So what happens if we take the inner product of this vector with 1, 0? Well, we just get x, right? What happens if we take the inner product of this with -1/2 root 3/2? We just get minus x over 2 plus root 3y/2. What am I saying? Ooh. Minus x over, yes, that was right. Okay. Minus x over 2 plus root 3y/2. And then similarly with this, we get minus x over 2 minus root 3y/2. Okay, so what is the definition of frames A? What do we want to do? We want to square up each of these inner products and sum them up. So if we square these up, we get x squared plus x squared over 4 plus 3y squared over 4. I'm going to leave out the cross term because since this is positive, this is negative, it's going to cancel out. And in fact, because of that, get
Yeah.
2 times this, right? So if we square this and add it to the square of this, then the cross terms cancel out, and we just get this right here. So what do we have? Well, we end up getting 3 halves x squared plus 3 halves y squared. So we just get 3 halves the norm of this vector squared, which by the definition we have up here, that means we actually get a tight frame, because no matter what vector we choose out, when we take the inner product with each of these elements, square that up and sum that out, we get an exact multiple of the original norm, regardless of where we started. And once you have a tight frame, it's very easy to get a parsable frame. You just divide out by this factor right here. So if we now multiply each of these things by square root of 2/3, then that's going to come out from here. It's going to come out as 2/3 and cancel it out. So obviously this is not an orthonormal basis. But the nice thing about something that's a parsable frame is you also get if we start with a parsable frame, for a Hilbert space H, then for all elements of that Hilbert space, we have that element is reconstructed so not only do we get this, that the norms are actually equal, we end up getting this nice reconstruction right here. So it means basically we've built redundancy into the system, right? So for example, here we now are representing things with 3 rather than 2. So if one is mitigated or one is deleted or something, it's not as big a deal as if one of the elements of the orthonormal basis was deleted. But if we know all of these coefficients right here, we can actually get the exact vector back. So this is why parsable frames are nice. They act a lot like orthonormal bases, even though they're not necessarily orthogonal or unit length, or even bases. So this is why they're nice. This is why parsable frames are desirable. And once you have a tight frame, it's basically the same thing. You can just scale. General frames, like there are definitely things you can do with what's called a dual frame. But so you can get a similar type of reconstruction, but it's a little more complicated. But a parsable frame gives you what you like about orthonormal bases. And if this is an infinite set, then you also get, with any sort of frame, that you can switch the order of summation, like it was like an orthonormal basis. You don't have to worry about what order you're summing things. Which when you're summing things over infinite indices, you do have to worry about that kind of stuff. Okay, so just go back right here, just a quick moment. So basically, Dr. Benedetto and some of the students at some point came up with this construction. It's iterative, and it's a machine that spits out wavelet sets. So you start off with a set that's translucent or tau congruent to the 0, 1, and you define this function that shifts things around, and then you go through this process, and you turn it out, and at the end what you get is a wavelet set as long as this function and this set, what you start off with is fine. Huh?
I have a question. So we don't expect the unit vectors, I suppose, base vectors to be orthonormal, but are there situations where maybe we can choose most of them to be orthonormal?
It I guess would depend on how you wanted to represent your data. Because you could certainly, so for example, if let's say I was looking over R5, let's say. So I can split that off into a 2-dimensional and a 3-dimensional chunk. So for that 2-dimensional chunk, I could have kind of the typical orthonormal basis. Then for the 3-dimensional chunk, R4. So two of it I could have at the orthonormal basis, and the other 2 I could have represented by this. So
why would
you could do that.
I want such a situation?
That's what I'm saying. That I don't know why you would necessarily want to split these things up. I'm just saying you could if you so desired. Usually you want a frame that's somehow, you know, computationally efficient for whatever reason, and you kind of want things to be spread out. So there's something that Dr. Benedetto has done some work on called cross-Montians, which basically means that, so if, let's say you lose the coefficient corresponding to one of the frame elements. So if you lose that coefficient, no one coefficient is more important than any other, basically. So if you were to have that other example where you had part orthonormal basis for 2 dimensions and part frame, then the two vectors representing the orthonormal basis section of it would be more important, right? So if you lost one of those, you would lose more information than if you lost one of these right here. So in a situation like this, it's kind of easy. Well, like this, obviously, you get this kind of equal importance amongst all of them. It gets very tricky in higher dimensions, even 3 or 4 dimensions, trying to get this quality of weight towards erasures. Like, you want to make things equal, and it's kind of an open problem basically to characterize the dimensions, the size of the frames corresponding to the dimensions, and basically the best you can do, because it ends up with some dimensions over some dimensions, or with frames of certain sizes, that you can't get something that's perfectly equal, but you want to try to get the best possible, right? So that's kind of an open problem, is figuring out these best possible frames when it comes to resiliency to erasures.
So were you asking like why you would want to say an orthonormal basis for like one subspace and the other subspace you have like a frame?
The reason I asked this question was, say you want to discretize an operator in some basis.
Okay.
You see, if you try to get a finite dimensional version of an operator, you turn it to a matrix in a basis, right?
Okay.
Maybe you could use frames for such a purpose, but
I think you can, but, and I believe, I mean, I just haven't read any of the papers. I mean, I feel like, but this is, I basically, I feel like almost everything that people have done with bases in math theory, people have at least tried to apply frames to. So I don't know if people have done it for sure, but I think they have, but I don't know if it yielded any beneficial result with that particular purpose. Are you about to say something, Nate?
Yeah, I guess you can do this because of the reconstruction formula that you acquire with a frame. I mean, essentially, when you discretize an operator in, say, an orthonormal basis, you're basically relying on this reconstruction formula. And so basically, via the reconstruction formula, you can discretize it in terms of a frame as well. And it's probably more robust when you actually apply the discretization, because frames kind of create a more robust system.
So anyways, not getting into too much detail with this, they have this nice construction. But it ends up that if you stop this construction after a finite number of sets, then what you get is a parsable frame. So now this algorithm that he has can actually be used to construct parsable frame wavelet sets. Okay. So that Journey wavelet set, there's a construction that can be, actually this isn't important, we'll slow this one out. Okay, so the next question is, all right, we would like to figure out, because what we're going to do is we're going to start with this parsable frame wavelet set, and we're going to do some sort of smoothing operation on it. So we're going to, it's no longer going to be parsable. So we basically want to figure out how far away from being parsable is it. So basically, we're not getting exact reconstruction, we're going to get some wiggle room, and we want to know how large it is. Obviously, the closer we get to exact reconstruction is preferable. So how do you figure this out? If you have a function, how do you figure out, well, what are the frame bounds? If I generate a wavelet system, how do I get the frame bound? So there are a couple of results that can help you do that. So one is Dobeshi's Christensen bounds. So basically, we define this auxiliary function. So we look at the Fourier transform of the function, and we do all the dilations with shifts, and sum that all up. And we look at the essential supremum, which is the almost everywhere supremum, if you're not used to that terminology. If central supremum right now is finite, then what we get is a Bessel sequence. That's when that upper bound exists on the frame. And in fact, we can even say that this is an upper bound for the frame bound. So whatever that optimal frame bound is going to be less than or equal to whatever this number is. You see why this is going to be nice, because if we're doing all this stuff on the frequency domain, and we're doing these computations on the frequency domain, so that'll help us a lot here. We similarly define this function. So this is basically the same thing as this, although now we subtract off all the cross terms. So everywhere where this isn't 0, instead of now adding those terms, we're just subtracting them off. And, okay, you can't see this, but basically you look at the inf of this, and if it's greater than 0, then you end up getting a frame, and the inf of this is going to be bounded below the, the lower frame bound. So here is bounding the frame bound on the other side, and this is due to Tui, Shi, and Jing. So now we have this other somewhat similar looking formula. Now we've thrown away all the cross terms. We're only looking at what happens with the dilations. And if we get a wavelet frame, so the other one showed us that we had a wavelet frame. But if we get this is a wavelet frame with bounds A and B, then this function for almost all gamma is between the frame bounds right here. So we can put this together and say that, so if we have that m of psi is less than infinity, then we get a Bessel bound where this frame bound is between that m of p and is greater than or equal to the central supremum of this. And similarly, we can get the lower frame bound is between the lowest value that this takes and that constant from the previous slide. So this gives us a nice way of estimating what our frame bounds are. And as I will show later, if we're very smart about this, they'll actually tell us exactly what the frame bounds are. Okay, so just a okay. Well, these are interesting, so I'm just going to go ahead and mention this. An approximate identity. So an approximate identity. So why is it called an approximate identity? So you guys worked with convolution? Yes? Okay. So you should know that there isn't a function f such that for all g in L1, meaning under convolution there's no function that acts as the identity. So there is something that does act an identity, but it's not a function, it's a distribution, it's Dirac delta. So, but what we want to do is, when we actually want to be able to compute things with functions, we use what's called an approximate identity. So it's a family of functions, basically that as you go further and further along in that sequence, you're getting closer to the Dirac delta function. So go ahead and go to the next one, because there's a nice generalization, or nice characterization here. If you have an integrable function, it integrates without the bars to 1. So it integrates finitely with the bars, and then without the bars, it also integrates finitely to 1. And then we look at this sequence of dilations right here, then the following assertions hold. We get an approximate identity, and for any f in any LP space, other than L infinity, we get this nice convergence right here. So that means it's acting, this sequence is acting like an identity not just for L1, but for all of these other LP spaces. So that means it's very good for approximating what we want. And if k is an even function, then we kind of can throw this stuff around here and say what we get is this function back pointwise. So why do we care about this? So one of the ways to smooth a function is with convolution. So what happens so if I have a function like this is my f, and then let's say let's say I just convolve f with itself. So then f star f is loosely going to look like something like this, kind of a pointy hat. So we started with this 0 and 1. We convolve this with itself, and we get something that looks like this. So what we've done is we've increased the continuity. Here it's not even continuous. It has jumped its continuities. Here we've got it's continuous, but it's not differentiable everywhere, right? And all these points are not going to get differentiable. And if we keep convolving f of itself, we get something that's smoother and smoother and smoother, more and more differentiable. But it doesn't have to be just convolution with itself. So, you know, if we have a, let's say here. So let's say we have some function like this, g, which is already a lot smoother, then we're going to get something more, well, okay, that looks about the same. But the idea is here that if you take a function and you convolve it with something, you're always increasing smoothness in some level. And if you convolve it with something that's very smooth, then you get something very smooth out. So if, for example, we have this as like infinitely differentiable, then what we're getting is infinitely differentiable. So why are these two things together important? Well, what we want is we want to take these Parsifal frame wavelet sets. So they're characteristic functions. They're 0 or 1 for all of their values. They're highly discontinuous. And we want to do something to them that will smooth them out so that on the time domain, temporal domain, there's better decay, but we don't want to lose too much of that reconstruction property. So what we're going to do is we're going to use these types of approximate identities to smooth things so that we're still convolving, so we're getting smoothness, but we're getting functions that are approximating our original function.
I just wanted to throw in a comment. I remember seeing something like this on Wikipedia. It's some Wikipedia smooth functions or smoothing functions, but there's a specific example of that kind of a function with compact support and smooth everywhere. It's some exponential thing. I don't forget what I'm just noting. I've seen that before. If you guys want to.
So there are actually a couple of different ways that you can construct a function. So this would be the notation for that. It's infinitely differentiable and compactly supported. All of the, or not all, I can say all, because I'm about to mention, at the end of the talk I mentioned another example, but most of the examples are somehow built on this function f of t that is e to the minus 1 over t for t greater than 0 and 0 otherwise. So this function kind of looks like this. And it is infinitely differentiable, even though possibly something could go wrong here. You do a lot of L'Hopital's rule if you actually want to do it by hand. You don't, but Dr. Benedetto did make me do it in the first class I took with him. But anyways, so you can do it. It's possible using basic calculus to show that this thing is infinitely differentiable. And so what happens if it obviously is not compactly supported? So the construction, there's a couple different kinds of constructions. But you basically find some way to kind of fold this function in on itself. And so you're kind of almost like getting this piece and then another mirror image of this piece and somehow forming something together that will make it.
What I remember of that construction is that polynomial in the denominator, 1 over t, you can just make that something like t squared minus 1 or something.
Right,
so you're 0, you just make it 0 wherever you want it to be 0, and then just zero it out from there out to infinity. I think that's what the construction I saw on the web.
One of the ways of doing it is replacing this denominator with something else. Another way of doing it is by making a